Now we have a question that says that a train has a maximum speed of 20 meters per second, which it can reach with a uniform acceleration of 0.25 meters per second squared. With brakes fully applied, it can decelerate uniformly at 0.5 meters per second squared. What is the shortest possible time for the train to travel between two stations 800 meters apart if it must stop at both stations? Okay, this is a very logical question, and the way I'm going to solve it is to use velocity time graph. So let me try and picture this using velocity time graph. Now we have two stations that are 800 meters apart, 8,000 meters apart, pardon me. So we have two stations that are 8,000 meters apart. I will take this point as point A. So this is point A, the first station, and I will take this as point B, the second bus stop. Then the distance between them is 8,000 meters. Now let's say that it started from rest, obviously, because the question says that it must stop at both stations. So it's accelerating from this point. Let's assume that it's accelerated to its maximum speed, and the maximum speed was given as 20 meters per second. So this is the maximum speed, 20. This is velocity time graph, mind you. So velocity on the y-axis, and this is time on the x-axis. Now let's say the time was enough. The maximum speed it can have is this. If time is enough, that means it's going to maintain this speed for a particular time, and then when the brakes are fully applied, it should stop at this point B. So this is deceleration. We do not know the time it takes to accelerate. We do not know the time it takes to decelerate. What we are looking for is the shortest possible time. So that means the shortest possible time must be the time it takes to accelerate and the time it takes to maintain this speed plus the time it takes to decelerate on full application of the brakes. What we know is that the maximum speed is 20, and then the acceleration, which is the slope, is 0.25 meters per second square. What I would do is to calculate the distance it traveled to accelerate. So for the first part of the motion, let's find the distance. That means we are going to have v is 20, u is 0. Since starting from rest, acceleration is 0.25. Then I'm looking for the distance it takes to accelerate. So I can say v square equals to u square plus 2es. And this is going to give me 20 square equal 0 square plus 2 times 0.25 times s. So s is 400 over 2 times 0.25 is 0.5. And 400 over 0.5 is 800. So for the first part of the motion, the distance covered is 800 meters. Now, I do not know what is going on in between the motion, but I know that this object is decelerating to rest, and we have the magnitude of the deceleration. So for the deceleration part, the deceleration is 0.5 meters per second squared. So this one is 0.5 meters per second squared. And since it's going to come to rest, I'll put the deceleration at this point. It's coming to rest. We know that v is equal to 0 meters per second. U, this will be the initial speed when it's decelerating. U is equal to 20 meters per second. We have the deceleration to be 0.5 meters per second square. Then we can find s. So we have v square equals to u square plus 2es. V is equal to 0. U is 20 square. I'm going to change this to minus because it's decelerating. So we have minus 2 times 0.5 times s. 0 square equals 20 square is 400. Minus 2 times 0.5 is 1 times s. So add s to both sides. S equal to 400 meters. So the distance covered for the deceleration is 400. That means the distance is this object is going to cover when it maintains the speed will be 8,000 minus 800 plus 400. So this distance in between is equal to 8,000 minus 1,200, and that is going to give 6,800. Now that we have more parameters, the best we can do then is to find the time it takes to decelerate, the time it takes to accelerate, and the times this object maintains this speed. So let's start with the acceleration. For the acceleration part, for the first one, we are going to use v equals to u plus at. V is 20, the initial velocity is 0, then plus acceleration is 0.25, so 0.25 times t, and this is going to give us t equals to 20 over 0.25. So t equal 80 seconds. Or let me say t1. So t1 is equal to 80 seconds. So that is the time taken for this object to accelerate. Now for the second part of the motion, distance covered for the second part of the motion is equal to 6,800 meters. The speed was constant, so it maintains a constant speed of 20 meters per second. So if we have constant speed, you can say that v equals to distance over time. Time will be distance over velocity, and distance over velocity, since the distance is 6,800 over velocity is 20, so 6,800 over 20, that is equal to 340 seconds. So I'll call that T2. So T2 is equal to 340 seconds. Now the last thing to do is to calculate the distance is going to use to decelerate. So calculating the distance, calculating the time it takes to decelerate, that means we are going to use v equals to u minus 80 because it's decelerating. The final velocity is 0, initial velocity is 20, minus the deceleration is 0.5, so 0.5 times t. That means we have 0.5 t equal 20. Then t will be 20 over 0.5, which will give 40 seconds. So T3 is 40 seconds. So the third time is 40 seconds. So what we did is we calculated the time it takes to accelerate. We calculated the time for it to cover 6,800 seconds. Then we calculated the time it took to decelerate. That means the shortest possible time now will be T1 plus T2 plus T3. So shortest possible time will be 80 plus 340 plus 40. And that is going to give 460 seconds. So the shortest possible time is 460 seconds.